In the last video we looked at the procedure of convolution between two functions. So let's say ft and gt they were, and the convolution was defined like this mathematically. So 0 to t f tau, where tau is a dummy variable, times gt minus tau d tau. This was our last video, and here we had to do an integration to find the convolution, but there's a convolution theorem that states that the convolution of two functions is equal to the inverse Laplace transformation of the product of Laplace transformation of the two functions, Laplace transforms of the two functions. So capital Fs, uppercase Fs, is the Laplace transformation of ft, and capital Gs is the Laplace transformation of gt. So the product of those two, of the transformed version, and then we find the inverse Laplace transformation. If we do that, we get the convolution of the two functions, the original functions. So we will do an example. We will do the one that we did before in the previous video. So ft was t in that one, and gt was sine t. In the previous video we did that, the convolution, and the convolution was ft gt was t minus sine t. Please check the previous video, we did that. So here we will apply the convolution theorem. So what we will do, we first want to find Fs. Fs will be, of course, 0 to infinity e to the power minus st t dt. I won't do the integration. I will just use the table which is available in any relevant book. Also you can Google it. So what's the Laplace transformation of t? That one is 1 over s square. And Laplace transformation of sine t will be, if it was sine at, Laplace transformation of that would be s square. For sine at it would be sine s square plus a square over actually a square over s square plus a square. But for our case a is 1 because the coefficient of t is 1, so gs will be 1 plus s square plus 1. So fs times gs is 1 over s square times s square plus 1, like that. Now in order to find the convolution, we need to find the inverse Laplace transformation of that, and we can say readily what is that. So what we will do, we haven't done any video on the procedure of finding inverse Laplace transformation, but I will do it here. So the thing is that when we are stuck up with such an expression, what we do, we try to expand it using partial fraction expansion, and we see if we can get something of which inverse Laplace transformation we know. So can we after the expansion, if we get some into some terms where their inverse Laplace transformation is readily known basically. So I will expand this one using partial fraction expansion. So I can say a over s square plus b over s plus cs plus d, since it's s square plus 1, like that. Then I will multiply both sides by s square, by this one basically. So the left hand side becomes 1, the right hand side a times s square plus 1 plus b times s and s square plus 1 plus cs plus d times s square. Now I will get rid of the brackets. So this is here as square plus a, plus we have bs cube plus bs, and then we have cs cube plus ds square, So I will write the coefficient, so I will write the powers accordingly. So I will separate the coefficient. So I'm just writing like this basically. A plus b s times s cube plus we have a plus ds square plus bs plus a. That's what we have. Now first we equate the coefficients from the left hand side and right hand side. When we equate that, there is only one coefficient here, the constants. First we are equating the constants. On the left hand side it's 1, and on the right hand side the only constant is a. So a is equal to 1. We readily get that. We readily find that. Now we will equate the coefficients of s basically. So on the left hand side the coefficient of s is 0, and on the right hand side the coefficient of s is b. So b is 0. We are getting that. Then we will do we will equate the coefficients of x s square. On the left hand side it's 0, on the right hand side it's a plus d. So we know so d becomes minus a. Now we know a is 1, so d is minus 1. We get that. Finally we will equate the coefficients of a plus b. So that's 0 here. Actually we don't need to do that because we already have everything. We have d is our minus 1, a is 1, b is 1. We don't have c yet, do we? And why don't we have that? Oh, actually it will be c here, sorry, a plus c, because the coefficient of there should be b plus c, sorry. I did a mistake there. That should be the coefficient of s cube. Coefficients are b and c, so that should be b plus c. So I will equate the coefficients of s cube as well. So on the left hand side it's 0, on the right hand side is b plus c. So b is equal to minus c. Now b is 0, we got that, so c is 0 as well. Now we have everything. We know a is 1 and d is minus 1, b is 0 and c is 0. So that's what we have. So when we do the expansion, it becomes x squared plus 1. This becomes 1 over s square because a is 1. If we go back to the original one, we will have only this term, and we will have this term with d as negative. C is 0. So we have minus 1 because cs plus d, c is 0, so s term is gone, d is minus 1, s square plus 1. So that's what we have now. This is our Laplace transformed version of, so basically this is what, just a reminder, this is this one. This is an expanded one. Now we know that when we want to find the inverse Laplace transform of this one, we actually can find it because we know the inverse Laplace transformation of this one, and we know what is this one, and this one is, if we look up the table, we can actually, we did that before, it's the same thing. So when we do the inverse Laplace transformation of 1 over s squared, that's t, and this one is sine t. Remember, that's what we did. So it has become the same thing actually. So t minus sine t, but we were multiplying then, and after the expansion we got them as a subtraction. So t minus sine t we get as the inverse Laplace transformation of the Laplace transformed product basically of the two functions, and this is the same as the convolution as we got using the conventional integration here. This is what we got. I think I wrote it here. Yeah, we did in the previous video. So this is exactly what we are getting using the convolution theorem. We are finding the Laplace transformation of each of the functions. We are multiplying those two, and then we are finding the inverse Laplace transformation of that product, and that will be the convolution in the time domain, because once we do inverse Laplace transformation we go back to t domain. So yeah, in the original domain. So yeah, so what we can achieve using the convolution theorem is we can avoid doing the integration basically. So yeah, this is just an example of the convolution theorem.